So let's slow down here a little bit. So the whole point of using these locations on chromosomes, these loci, is that the odds of any two people matching a particular location, an allele there, is unlikely. This is 7.5%. The odds of matching two of them, even more unlikely. Three of them, even more unlikely. Matching for you and I to have the same alleles, that is the same repeating, same number of repetitions of those phrases along the chromosome at 6 locations, would be about 1 in 5 million. That's pretty rare, right? And we saw from earlier that if you're doing, if you have 13 here, it's about 1 in 500 trillion. So in principle, it's a very good system. It does a very good job. So if these are the odds, why would you find lots of matches in a small database? This is what happened. There was a small database of 65,000 criminal profiles, and somebody was doing something, and they found a bunch of them matching at 9 places. Well, this looks extraordinarily unlikely by the FBI's probabilities for the frequency of these variations, these allele variations. That's a 1 in 10 billion. How could you possibly have lots of matches in a tiny database? Well, this is the birthday problem all over again. And the question is resolved by thinking about how many pairwise comparisons can you make between 65,000 people. This is exactly like the birthday problem, but with 65,000 people and different probabilities. The probability is this probability of a match at a particular allele. Well, the formula I've given you for the number of pairs, so this is the number of pairs formed from n plus 1 people. Right. And the plus ones and stuff barely matter here. So we don't even have to worry about that. We can kind of willy-nilly use this as 65,000. 65,001 divide by 2. How many pairs is that? So I'll use the handy-dandy calculating machine. So this is 2.1 times 10 to the 9th power. So that's 2 billion. That's a lot of possible pairs. However, it doesn't seem to be quite enough. There's an extra part here. And so at this point, if you were to multiply this database by that probability, and let me do that. So if you took 2.1 times 10 to the 9, you multiplied it by, whoops, you can't see what I'm doing, by 7.5 times 10 to the minus 11, you would get, you wouldn't get a whole number. So let me run that for you. So you get 0.15. That's not a whole person. This is less than one person. It's not a lot less than one person. It's surprisingly high. So you might say, well, okay, I can imagine then maybe finding a single match. There's actually more, though. Here's the idea. This is a bit tricky, and if you don't get this part on the exam, it's okay. If you can explain this well, there'll be a bonus point. So here are 2 people, person 1 and person 2, and each of them have 13 locations. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 locations here. Now, each location there are 2 numbers. And this person also has 13 locations. Now, the question was, what is the likelihood of matching at 9 of these? Well, we don't have to necessarily match the first 9. We could, maybe it's the second 9. Maybe it's the first and the third and the fourth and the fifth, and then skip the 6th and the 7th and the 8th, and then 9, 10, 11, 12, 13. So the idea, when you're comparing these 2 people, there are actually quite a few comparisons. It's not a matter of comparing all 13 with all 13. That would be looking for a total match. We're just looking, are there 9 matching loci between them? And this actually requires a wee bit more math, and again, this is bonus point material. So between 2 people with 13 loci, how many ways can you pick 9? How many different ways can I choose 9 of these positions and then check them against this? Obviously, I can choose, 1 through 9, 2 through 10, 3 through 11, 4 through 12, 5 through 13. But I can also do 1, skip 2, 3 through 10, and so on. So how many different ways can I do that? Well, there's a way of figuring this thing out. If you have 13 objects, and you want to choose 9 of them, actually, there we go. And this exclamation point is called a factorial. I know some of you will know what this is. Yeah, it's not just loud math. Right, so 13 factorial is not just 13! Right? Not quite. 13 factorial is 13 times 12 times 11 times 10, all the way down to 1. It's a gigantic number. So this number, 13 factorial, ends up being like 700 and something, I think, if I remember right. Whoops, my computer went silent. There we go. And you can actually calculate that on most calculators. My calculator, it will have numbers in different places than yours, but you should have some exclamation point somewhere in your calculator. So 13 factorial divided by, I get a 9 factorial times, this is going to be a 4 factorial, gives me 715. Right? So this is kind of mind-boggling. So between these 2 people, there are 715 ways to compare 9 spots. So let's go back to where we were a minute ago. There are 2 billion ways to pair these people off. And for each of them, there are 715 ways to compare 9 positions in their DNA. So that's 2.1 times 10 to the 9 times 715. So these are pairs among 65,000 profiles. And these are ways to compare 9 loci from each pair. And this ends up being a big enough number. So if we multiply this by 2.1 10 to the 9, now we have 1.5 times 10 to the 12, about 1 trillion. Well, our probability before, so this is the number of possible comparisons. And the odds of a single comparison yielding a match at 9 locations is this. Okay? This is a smaller number. So now if we multiply these two numbers, so 1.5 times 10 to the 12, this is the number of comparisons between 65,000 people at 9 loci times 7.5 times 10 to the minus 11. This is the odds that a given set of 9 loci match the same 9 positions in another person. So what does this end up being? All right, well, let's run the numbers. So I'll multiply this number by 7.5 times probability. Whoops, syntax error. I delete that. And then this ends up equaling 1.12 times 10 to the 2, which is 112. So let's pause and take this in. With 65,000 people, there are several billion ways to pair them up. For every one of those pairs, there are 715 ways to compare 9 out of 13 positions. The product of those two things give us 1 trillion ways to compare 65,000 people, 65,000 DNA profiles at 9 out of 13 spots. So even though the probability is just under 1 in a trillion, you would expect to find about 112 matches. And in fact, they did. And if you do this for 10, 10 loci and 11 loci and 12 loci, it's possible to find those as well. So this is not stuff you're going to have to use when you're grocery shopping or surfing social media. But I do think these numbers are crazy numbers. In fact, there have been some legal theorists that have talked about how they shouldn't even be admitted into court. They're talking about 1 in a trillion or 1 in a quadrillion. You're just snowballing the audience, the jury. Nobody understands these numbers. And if you find them difficult to understand, you're in good company. But we do read about legal cases. We sometimes watch them on TV, as the case of O.J. Simpson. We're confronted increasingly with quantitative information and with very big numbers. I showed you pictures of $1 trillion, and it was amazingly large. And the difference between 1 million seconds and 1 billion seconds was the difference between a week and a half and almost 32 years. So these big numbers are hard to comprehend. And we clearly make mistakes, and it's not because we're dumb. It's because the right path is very difficult to ascertain. It involves very careful language and careful calculations. But these are the difference between people being convicted or not convicted. Bad people getting free, innocent people being convicted. So sometimes numbers matter. And I think this is at least a context where you can see that these calculations make a difference in people's lives. John Puckett was convicted because it's okay to have 112 matches at 9 loci in this database. If the prosecution hadn't answered correctly, the defense might have been able to argue that the frequencies are incorrect, and he might have been not exonerated, but acquitted. Right? So, was he guilty or not? We can't know. But the frequencies do seem to hold up. This is what was found based on the FBI's frequencies. So they're probably not exaggerating them. Okay, it's a lot of video. So have a nice day.